If you're engaging with AI right now, pulling up a search result, doing a reverse image search, anything like that, you're relying on one core component, vector embeddings. Every piece of data, whether it's text or an image, gets turned into this dense high-dimensional vector. But, turning data into vectors is only half the battle. The real immediate challenge is speed. When you have billions or even trillions of these numerical points, how does the system instantly find the closest vectors to your query? That kind of scale demands some very specialized tooling. So today we're doing a deep dive into the source material around the FAISS library. This is a critical open source C++ toolkit for what's called approximate nearest neighbor search, or ANNS. Our mission here is to unpack the design principles, the really critical trade-offs, and the ingenious techniques FAISS uses to make billion-scale similarity search fast and accurate. And one of the first things you notice about FAISS, and this is a big part of its power, is that it's deliberately limited. It's not a full database. It doesn't do networking or transactions. It's a specialized, pure algorithmic engine, and its strength is its ability to combine dozens of optimized methods for just one purpose.
That specialized focus is absolutely key. As you said, it all starts with embeddings. And just to be clear what those are, they're vector representations from a neural network where the distance between points encodes, the semantic relationship. Closer vectors mean more similar words or more similar images.
Right.
And the sources bring up this concept called the embedding contract. FAISS is all about fulfilling the second half of that contract.
Okay, what's the first half?
The first part is the neural network itself. It has to align the distance metric like L2 distance to the actual task. So it makes sure that distance really does correlate to similarity.
And the second part is FAISS.
The second binding part is that the vector index FAISS has to perform that neighbor search as accurately and quickly as possible, given that specific metric.
Okay, so let's unpack that core tension right away. Speed versus accuracy. If you want 100% accuracy, you just use brute force.
Exactly.
The baseline for this in FAISS is an exact search, right? They call it index flat.
Yep, index flat. It just iterates over every single one of the n database vectors to find the nearest neighbors. It's perfect.
But completely prohibitive if n is in the billions.
Precisely, which is why we need approximate nearest neighbor search, or ANNS. The moment you go down that path, you're agreeing to accept imperfect results for huge gains in speed.
And that means managing a trade-off.
A critical trade-off triangle, really. You have three performance axes to balance. First, there's accuracy.
Which is measured by n recall at k.
Right, which is just a fraction of the true nearest neighbors your system actually finds. You might happily settle for 95% recall if it makes the query 1,000 times faster.
Okay, so accuracy is one. What's the second?
Raw speed, queries per second. And third, the one that often limits the first two, is resources. So memory usage, how long it takes to build the index, all that overhead.
And what's really fascinating here is how FAISS handles the distance metrics themselves. We talk a lot about L2 distance, which is the default.
But it also supports cosine similarity, which is key for normalized vectors, and maximum interproduct search MIPs, which you see a lot in recommendation systems.
This next part from the source material was a real aha moment for me. The idea that L2, cosine, and MIPs can all be used interchangeably by the core engine.
Yes, that's the mathematical elegance it leverages. The sources show how they can all be made equivalent through some simple pre-processing transformations.
What kind of transformations?
Often it's as simple as adding one or two extra dimensions to the vectors. This really highlights a core design principle. FAISS keeps its indexing algorithm standard and uses these transformations to handle different user needs.
So if you're deploying this, you have to find your perfect balance point. You're not just looking for good settings, you want the optimal ones.
Exactly. You're looking for the Pareto optimal settings, the configuration that gives you the absolute fastest speed for a given accuracy or the highest accuracy for a set time budget.
But that search space must be enormous.
It can be. The example in the source material had over 5,800 combined parameter settings. You can't test all of those.
So how does it avoid that?
It uses efficient pruning. Since the parameters are usually monotonic-like, a higher search setting means slower speed, but better accuracy. For me, just explore the boundary of optimal performance.
And that cuts it down.
In that 5,800 combination example, it cut the necessary experiments down to just 398. That's how you can actually find the optimal trade-off in the real world.
Okay, let's move on to the first major tool in the toolkit. Vector compression. If you have 1,768 dimensional vectors, you can't store that in RAM uncompressed.
Not affordably, no. Compression is mandatory. The goal is to represent the vector with a short fixed-length code and minimize the reconstruction error.
And the ideal method, a k-means quantizer, is basically out of the question.
Immediately. It's just too computationally heavy beyond, say, 3-byte codes, which only gives you 16 million centroids. We need something way more scalable.
Which brings us to the practical world of quantizers. And FAISS has two main families. Let's start with the one that gives you the most bang for your buck on speed, product quantizer.
The product quantizer, or PQ, is a real workhorse. Imagine your 768-dimensional vector. PQ splits it into smaller, non-overlapping subvectors, maybe 16 subvectors of 48 dimensions each.
And it quantizes each little piece separately.
Exactly. It generates a short code for each subvector. To reconstruct, it just concatenates them. That's why you see notations like PQ6x10. It's a great trade-off because encoding is fast and the accuracy is pretty reasonable.
That makes sense. A good balance. But what if memory is the absolute #1 constraint? If you have the lowest possible memory budget, you need something more accurate, even if it's slower to encode.
And that's where the additive quantizers, or AQ, come in.
Right.
These are more complex because they try to fit the data much more precisely. The key difference is, instead of concatenating codes, they sum the reconstructions from multiple smaller quantizers.
The simplest one is the residual quantizer, RQ. How does that work?
It works sequentially. It encodes the vector, then it calculates the residual, the error between the original and the reconstruction, and then it encodes that residual. And it keeps doing that until the error is tiny.
It's like an artist sketching an image and then sketching the difference between their drawing and the photo, over and over.
That's a great analogy. And the local search quantizer, LSQ, is the next level up from that.
How so?
LSQ uses a powerful optimization technique called simulated annealing. It basically explores neighboring codes to find a near-optimal encoding, really trying to get the best possible fit for a very small code size.
So the key takeaway for you, the listener, is this choice. Need the fastest encoding. PQ is your friend.
But for the smallest memory budget, where you need high accuracy on a really short code, the additive quantizers, RQ or LSQ, are usually the superior, though slower, choice.
And crucially, FAISS lets you pre-process the data before you compress it. You can run PCA to shrink the dimensions, or if you're using PQ, you can run something called OPQ.
Right, OPQ rotates the input space to decorrelate the subvectors, which makes the product quantizer work much, much better. It's all about setting the stage for the compression to be as effective as possible.
Okay, let's pivot from memory to speed, non-exhaustive search. If your database size N is over, say, 10,000, compression alone isn't enough. You need shortcuts.
You have to avoid checking all those billions of vectors. And FAISS focuses on two modern approaches here, starting with inverted files, or IVF.
This is a partitioning method.
Exactly. At indexing time, you cluster the vectors. You partition the entire vector space into, say, KIVF neighborhoods. Each vector gets assigned to an inverted list.
When a query comes in, you don't check all the lists.
Right. You use a coarse search to find the closest, say, POVF clusters that's controlled by a parameter called nprobe, and you only search the vectors within those few lists. It's incredibly effective pruning.
The sources mentioned a really fascinating empirical scaling rule for IVF.
Yeah, the complexity analysis is impressive. For IVF indexes, the search time's dependence on the database size is well below linear. It scales by a power less than 0.5, so it's sublinear to the square root of n.
So adding 100 times more data might only make the search 8 or 9 times slower.
Something like that. It finds shortcuts so efficient that it doesn't just grow linearly with your data. And that makes IVF the champion for truly massive compressed databases.
And for those, it's better to compress the residual, the error, not the original vector.
Exactly, because that residual encoding focuses on the fine-grained differences.
Okay, what about the second approach to pruning, the one that's often more accurate on smaller datasets?
That would be the graph-based indexes, specifically HNSW and NSG. These are totally different. They get rid of the coarse clustering and instead build a graph where every node is a vector.
And search is just walking along the graph.
Greedily traversing the edges toward the query vector, yeah.
So how do HNSW and NSG differ?
It really boils down to flexibility versus quality. HNSW, or Hierarchical Navigable Small World, is dynamic. You can add new vectors on the fly. Huge operational advantage.
And NSG?
NSG, the Navigating Spreading Out Graph, often gives you a better speed-accuracy trade-off. It's faster for a given accuracy, but it requires a long initial build time. And once it's built, It doesn't easily support adding new vectors. It's essentially a frozen, highly optimized map.
So if NSG is more accurate, why would anyone use HNSW? It sounds like you're just sacrificing optimality for convenience.
And that's the classic trade-off. The crucial index selection rule from the sources is this. If your data set is below, say, 10 million vectors, and memory isn't a huge constraint, graph-based indexes are fantastic.
High recall, great performance.
But for billion-scale inboxes where compression is mandatory just to fit the data, IVF is the only viable path. You trade that high-accuracy graph structure for the raw ability to handle immense scale.
Let's move into real-world engineering. FAISS is an engine, but it has to integrate with databases. It supports sequential IDs and also arbitrary 63-bit integer IDs.
All right, through something called index ID map.
But the operation that really complicates things is updates. If you remove vectors or if the data distribution changes, the index efficiency degrades.
Because the underlying clustering or graph structure is no longer optimal. To support lookup and removal by ID, FAISS has to keep this separate structure called a direct map.
Which is just pure memory overhead.
Exactly. It defeats the point of compression a little bit. But the biggest engineering challenge cited in the sources is filtered search.
This is when you need to find similar vectors, but only for items that meet some other criteria, like only products that are in stock.
And the traditional vector-first approach is agonizingly slow. The filtering check, an ID selector callback, has to run in the tightest search loop, and that causes cache misses and huge delays.
Which brings us to this brilliant technical hack from the Big N competition, the bit manipulation solution. How did they solve this at the CPU instruction level?
It's just an exercise in extreme efficiency. They looked at the 63-bit user ID. If you only have 10 million vectors, you only need about 24 bits for the ID.
That leaves 39 unused bits.
And FAISS uses those unused bits to store a binary signature of the vector's metadata. So instead of a slow database lookup, the system runs a machine instruction level check.
A bitwise operation.
A simple bitwise operation. It compares the bits in the query signature against the vector's signature. And because it's handled in a tiny fraction of a second inside the CPU register, it can pre-filter candidates before running the slow, full check.
So that one trick turns a database lookup into a single CPU instruction. That's the kind of efficiency gain we're talking about.
That's why it works at scale, and it also allows for a smart heuristic. The system estimates the size of the required subset. If it's tiny relative to the whole database, it just switches gears and does an exact brute force search on that small pre-filtered set.
The true demonstration of this philosophy comes when we look at the absolute limits of scale. The sources detail a real-world trillion-scale example. 1.5 trillion vectors.
1.5 trillion vectors, 144 dimensions each. It's an exercise in resource constraint. Compression is not optional.
It's mandatory. So first, PCA to reduce from 144 dimensions down to 72.
Then those are compressed down to just 54 bytes each using a 6-bit scalar quantizer. And this is followed by a hugely complex, multi-phase, distributed build process.
I want to spend a moment on that build process. It's in 3 massive phases. Why do they need to shard over IDs and shard over inverted lists?
They need 2 different sharding approaches. Phase 1, sharding over IDs, just breaks the data into 2,000 chunks to manage the raw volume.
Oh, okay.
Phase 2 involves sharding over the inverted lists. They build 100 separate indexes on 100 different machines at the same time. That parallelism is the only way to get through the computationally intensive training for the quantizers.
And then they have to unify all of that for search.
Which is an insane logistical challenge. Phase 3 is loading all 100 indexes, which, even with compression, still need a memory map of 83 terabytes onto a central cluster to handle queries.
So given this extreme scale, what are the most high-impact applications?
Content moderation is a massive one. Labeled examples of policy-violating images or videos are stored in a trillion-scale FAISS index. When new content comes in, it uses range queries to find similar violating content.
And the stakes are incredibly high there, so accuracy matters.
Exactly. You need massive scale and highly accurate search. Beyond that, you see FAISS in knowledge-intensive NLP, like fact-checking, and in data mining, like finding duplicate images in a 1.3 billion image dataset.
Wow. We've covered a tremendous amount of ground here, from the abstract embedding contract to the logistics of memory mapping 83 terabytes.
It's a lot.
To summarize this deep dive, FAISS is this critical, flexible toolkit that manages that eternal tension between speed and accuracy. It does it with sophisticated tools like inverted files and graphs, and clever memory tricks like product and residual quantization. Ultimately, what we've seen is that even with trillions of data points, the most important work happens when you figure out what data you can safely compress and what shortcuts you can take to ignore most of the search space.
That's absolutely right. And to leave you with a final thought to mull over, we talked about that index selection rule. It shows that some of the best performing index types, like NSG, get their peak accuracy because they're static. They don't easily allow new data to be added.
Right.
This raises a big operational question. When you're designing systems for rapidly changing living information,
Hmm.
how high should you prioritize instant dynamic updates versus getting the absolute fastest, most accurate search possible on the data you already have? That choice between static optimality and dynamic flexibility is going to determine the long-term effectiveness of whatever system you build.